few minutes today talking about some of the market segments that are critical segments for non-volatile memory and why we feel that OTP, one-time programmable memory, is a key driver in the semiconductor industry. I'll then talk a bit about Sidense's technology. It's an anti-fuse OTP technology, patented. Then discuss the product family we have, SHF, for advanced process node development, and finish up with an example using one of our SHF macros. If we look at the chart here and look at the left-hand side, these are some of the key driving forces within the industry today. First is low-cost options for secure digital content. And what everyone's looking for is a secure way of storing code and information, such as boot code, encryption keys, identification numbers, etc. And secure OTP memory is ideal for this type of application. In the center slot, we see calibration and trimming. Many of our customers use Sidense OTP memory for trimming and calibrating sensors and critical timing circuits, as well as other types of analog circuits on chip. And then on the right, our OTP is field programmable, and by using field programmable OTP in place of mask ROM, it gives you the option of being able to do firmware updates, software changes on the fly, without undergoing very expensive and very time-consuming mask changes, which can actually eliminate you from a certain market that you're trying to enter. So let's talk about why our 1T OTP, one transistor per bit cell, is a key ingredient for your silicon success. On the right here, in the figure, our bit cell is 1T fuse technology. It's a single transistor, 2 oxide thicknesses, core and I/O. And you program by putting a voltage on the thin oxide region, and once programmed, it is non-reversible, so it's very secure once it's programmed. We have very broad process availability, from 180 nanometers down to 20 nanometers at the moment, and this includes various variants of process nodes for BCD and high voltage applications for high temperature. Being a single transistor bit cell, our memory has a very small footprint. It's very cost effective, so you can find uses for it everywhere from high data density for ROM replacement, and again, field programmable, it gives you an advantage over mask ROM, all the way down to a very low power, very small memory for trimming applications or for encryption keys. Very secure and reliable. There is no charge storage involved in this memory bit cell, unlike flash. So the retention rate is very good, over 10 years at maximum temperature and 100% read duty cycle. That makes it ideal for secure keys and trusted zone applications. It's virtually impossible to reverse engineer. As I mentioned, once programmed, it stays programmed in a variety of mechanisms within the macros themselves, which also add increased security to the memory macros using this bit cell. And lastly, it's very, very flexible. It's field programmable, as I mentioned. You can use it for emulated multi-time programmable applications, and I'll go into this a little bit later. So what this means is, where normally you would use multi-time programmable technology such as flash, you may be able to use this. It's smaller, it's less power, it's less expensive. There are no process changes or mask changes from putting this memory on your chip. And ROM conversion is very simple. A single mask change, same footprint, you can convert to ROM. Okay, who are we by the numbers? We're a well-established NVM IP provider. We've been around for 10 years. We have over 120 engaged customers, more than 120 patents granted and pending, over 360 design wins, and we support over 40 process nodes with over 12 silicon foundries. Now, this is a chart showing the products we have available today. Looking at the bottom middle, we have SLP and ULP. These were developed initially for 180 nanometers, 3.3 volts. There are two variations of SLP, A and B, for high voltage and power process variants. SiFuse is another product family we have as an eFuse replacement. Another variant of SLP is C. This was developed for 90 nanometer high voltage, very similar characteristics for 180. On the left side in gray, SiProm, from 55 nanometers up to 130 nanometers, 3.3 and 2.5 volts. And then highlighted is HSF. This is the technology and the family we have for advanced process node development. It targets process nodes from 40 nanometers to 20 nanometers and beyond, and I'll give a lot more detail about this as I go along. The SHF is a true memory subsystem, not just a block of memory. You have an OTP hard macro, configured up to 1 megabit per macro, data widths up to 40 bits per word, including 8-bit ECC. There are various read modes available, so you can basically choose the compromises you want between read speed and area of the macro. You have available a charge pump, integrated power supply for in-field programming, and also supply some of the other internal voltages used by this macro that are derived from the normal chip voltages. And in addition, we have a device access port and a memory controller available in RTL code. Now, I mentioned earlier emulated multi-time programmability. What this means is you can take a macro that has more memory than you initially need, program part of it, and leave unprogrammed portions of it for future programming, for updating the information that you contain in the memory. This is good for code revisions, encryption key rewrites, and data updates in the field. It's a very small footprint. That's how you can do this. So you reserve sections of the OTP for updates as a simple write operation when you want to rewrite your data or update it. And there's no erase cycle required because the memory is unprogrammed at that time. There are power supply options available, so you can either do the programming with an external chip, or you can do it on chip. And it's, again, easy conversion to ROM. Simple mask change, same footprint. This example here shows an initial version of 512 bits. It's in a 16K macro, so you can rewrite it up to 15 additional times for updates. Single macro can be used for multiple uses. In this example, the red section on top is what I just described, 8 kilobits for 512 bits being able to be rewritten 15 different times, 16 times altogether. In the black section right below it, we have 8 kilobits of redundant memory, which this means is there are 2 physical bit cells for every logic bit. And the reason this is done is enhance security for field programming in system. Below that, 16 kilobits of single-ended, 1-bit cell per logic cell, programmable at the tester at the bench. And below that, 32 kilobits that can be converted to fixed code easily, so you can save time during test. 1 diffusion mask change. And in the 60 kilobit memory, you have 4 different uses. And if you want to do the mask ROM as shown here, you don't have to do all of it converted to mask ROM. You can convert just part of it. This is the example I mentioned at the beginning, using HSF for a wireless IoT processor. In this example, the SHF macro is in the upper right of the chip. The gray shows boot code for the application microcontroller. The green shows encryption keys and secure communication protocols for the wireless LAN controller and the RF front end. And then there are trim settings in yellow for trimming and storage and configuration circuits for adjustments and tuning during test, to allow for aging of the circuit, for timing critical circuits, and in-field adjustments when it's deployed, the system is employed in the field. This is a roadmap of where we're going with our OTP products. We already have several of our products qualified for TSMC 9000 at both 40 nanometer and 28 nanometer variants, several variants. We also are developing macros for another foundry's 28 nanometer processes. We have fully functional silicon at 20 nanometers, 1.8 volts. Has passed 1,000 hours of high temperature testing. And we are developing our macros for FinFETs at 16 nanometers and below. We have several business models that all entail single use and multi-use for licensing. There's NRE, maintenance, and royalties involved. We have different options for broad licensing to meet customer requirements. And from a deliverables point of view, we have a very broad range of comprehensive deliverables that provide a very high level of support for our customers. So, why should you remember Sidense? We have embedded NVM for standard logic CMOS processes. No additional process steps, no additional masks. We're the industry leader with a wide range of capability and features, as shown here. Very, very rich set. And we have macros available from 180 down to 20 nanometers, working on developing below 20, and we're scalable as far down, we're already looking at 10 nanometers. So I want to thank you for your time. I hope you'll explore our IP both on our website and on ChipEstimate.